right, so we are moving away from phase equilibrium, and we are going to be wrapping up our final topic before moving into statistical mechanics, and that is chemical reaction equilibrium. And I will oftentimes write this as CRE, just because chemical reaction equilibrium takes a long time to write. So, what we have focused a lot of our time on so far is vapor-liquid equilibrium, because it's one of the more common types of equilibrium that we're going to face. Liquid-liquid equilibrium, probably the second most common type that chemical engineers are going to face. Chemical reaction equilibrium seems to be something we should probably talk about because chemical engineers tend to do a lot of reaction systems. But take any of those and mix and mash them together, and then you've got a real modern process. So you can have liquid-liquid vapor equilibrium, you can have reactive distillation, in which case you're doing vapor-liquid equilibrium plus chemical reaction equilibrium. Now a lot of advanced chemical engineering classes, sort of an old school approach, will break it down and then we'll start talking about really, really detailed advanced scenarios of multiple different types of phase equilibrium or reaction equilibrium at the same time. But I find it to be somewhat uninspiring because the answer is you just derive a bunch of equations and you solve them all at the same time, right? So it's going to be a patchwork methodology in order to figure out, okay, how am I going to model the liquid-liquid equilibrium? How am I going to model the chemical equilibrium? How am I going to model the reactions? And you just have a patchwork of different modeling approaches, try and solve it all at the same time to figure out if you've got one steady state solution, and then you've got your problem solved, right? So what I would rather do instead is break it down into the individual building blocks and note that if any of you ever come into a situation where you have to model or understand a reactive distillation process, hopefully you've got the tools to understand the individual building blocks, if that makes sense. So what we're going to be talking about for chemical reaction equilibrium is the simplest case, which is going to be effectively ideal gas phase is going to be the most emphasized. But we'll talk about how you can do liquid phase and non-ideal systems as well, but the majority of the work which can be focused on ideal gas phase reactions. The key thing here to remember the equations of chemical equilibrium are the same. Nothing is going to change on the fact that we are breaking and making bonds. Everything that we've learned about thermodynamics is 100% consistent. Thermodynamics is appropriate for macroscopic systems. Thermodynamics is appropriate for microscopic systems. Thermodynamics is appropriate for classical. It's appropriate for quantum. It's appropriate for subatomic. Right? It's appropriate for everything. So whether or not we're dealing with electrons, bosons, quarks, whatever the case is, thermodynamics always holds true, which is nice. So in our case, nothing here is really going to change. The only thing that's different we're going to have some slightly new notations and approach. Just as how the Gibbs free energy was created as a convenience function to help us do phase equilibrium, we're going to be defining some other new functions that are convenient to allow us to solve chemical reaction equilibrium at the same time. So, with that being said, let's go over the notation of chemical reactions. Who here does not have a chemical engineering undergraduate? 1, 2 folks, okay. Rui, you have a chemistry undergrad? Oh, no, okay. Because you're in mechanical, right?
Material science.
Material science, okay. So, just so we're all on the same page, I will write an arbitrary chemical reaction. In this case, we'll do double-sided arrow to show that this is going to be in equilibrium. Right, we have a number of A-type molecules. This could be, let's say, water. This could be B, could be something else. C could be something else. D could be something else. The coefficients, these are called the stoichiometric coefficients. Right, the stoichiometric coefficients tell us how the rate of consumption of one side of the equation is related to the rate of formation of the other side. So if I were to look at this chemical reaction, I have 1, 2, 3, 4 components. So I have 4 unknowns, potentially, if I'm doing this reaction. Right? I have a chemical reactor, I'm feeding a bunch of A and B, I'm trying to figure out what comes out the other side. Do I really have 4 unknowns in this equation? How many unknowns do I have? The answer is 1. All of these are related. The rate of consumption of A is related to the rate of consumption of B, which is related to the rate of formation of C, which is related to the rate of formation of D. These are all connected through a variable that we call the extent of reaction. So we define a variable written by a big X, sometimes it's chi, I just write it as a big X, called the extent of reaction. Oh, sometimes, in a lot of chemical engineering texts, they do psi, which is this gnarly guy, I don't even know how to write it. Do you guys know what I'm talking about? I hate that one, so I just use a giant X. I call this the extent of reaction. The extent of reaction is basically a way that we can use for chemical reactions that tell us, sort of in a batch sense, what is the rate of consumption of the batch of products to create a batch of reagents to create a batch of products. Right? Just because we have a series of unknowns, they're actually all dependent on one another. Now the extent of reaction is where that dependency lies. So what we do is we write the stoichiometric coefficients here. Generally, we'll denote that with nu, the Greek letter nu sub I, indicating that I corresponds to either A, B, C, or D. So in this case here, the stoichiometric coefficient nu is going to be equal to, so let's say nu of A is equal to minus A. Nu of B is equal to minus B. Nu of C is equal to C. And nu of D is equal to D. We have a negative term for the reagents and a positive quantity for the products. This follows the same approach that we use for a delta function. Products minus reactants. Final state minus initial state. Right? This is just a convention we've adopted so that everything's consistent. It does not have to be the case. We could redo everything having a negative sign. And in fact, that's going to be exactly the approach that we're going to take when we're solving problems. When I write out a reaction, I don't actually know which direction it's going to go. That's going to be dependent on what the feed conditions, what the temperature conditions, what the pressure conditions are. But if we just adopt this system, then it's a lot easier for us to troubleshoot each other's work. But at the end of the day, if we screw this up and we flip this around, as long as you flip it around for all of your equations, you're A-okay. That effectively means you just switched the reactants and products. But since this is a reaction system, an equilibrium system, right, we don't care which side we're starting off on. So, what we do then is that we will write N is the number of moles of species I in our reacting system. N sub I naught we define as the number of moles of species I initially in the system. Now we can think of this either as a continuous steady state process or as a batch process. So if we're modeling the system as a continuous system, now me being a chemical engineer by training, I always think of things as a continuous process. To me it's just easier to do the math. And oftentimes it's a lot easier to do the math if you're doing a steady state process. Because if you think of a mole balance, right? You have dN dt, what's the rate of change of the number of moles? It takes away all the differential calculus. If you do things in a batch, so in this case here, this would be the initial or the in, this would be the final or the out. Another scenario is you could visualize lots of these in a batch. You can do both of these in a similar way. Now the course of reaction kinetics is basically entirely focused on this process here. But because we're a thermodynamics course, we don't actually care about how long it takes to accomplish any of these things. So in a thermodynamics course, these two are effectively going to be equivalent, right? It's the same thing as running a steady state process until it reaches its steady state operation, or running a batch process for a very, very long time. They're both going to be equivalent on a chemical reaction. So however you want to visualize these is entirely up to you. Now, what we're going to be writing then is we can write that the number of moles of species I in the system is going to be equal to the number of moles of that particular species fed plus the stoichiometric coefficient times by the extent of reaction. So what this is saying is that if I have no reaction, meaning my extent of reaction is 0, the number of moles of species I is going to be equal to whatever starts off in the system. It's really boring, nothing's happening. Now, if my extent of reaction progresses, and my reaction moves in the positive direction, so in this case here, this is going to be positive for a reaction moving to the right, and it's going to be negative for a reaction moving to the left. So right hand side reaction to left hand side. This is why it doesn't matter how we define our stoichiometric coefficients, as long as we're consistent. So, if my reaction progresses this way towards equilibrium, that means that I will be having a negative A, a negative B stoichiometric coefficient. Meaning here that if I'm looking at the number of moles of species A, in this case, number of moles of A is going to be equal to the number of moles of A initially fed minus stoichiometric coefficient of A, which is A, times by the extent of reaction. That means if I have a positive extent of reaction, I will be consuming moles of A. Likewise, I can fill it in, N sub B oops, this should be minus my bad, plus C X N B. Okay. Now let's say I screwed up, and that the reaction, actually the equilibrium should be pushed further to the left. Right? Let's say I have an equimolar quantity of A, B, C, and D. So 0.25 moles, 0.25 moles, 0.25 moles, 0.25 moles. Whether or not my extent of reaction is positive or negative tells me if I'm drawing my if my reaction is going to the left or the right. So if I have a negative extent of reaction, that means I'll actually be consuming C and D, and I'll be creating A and B. Right? That's the notation for chemical reaction equilibrium. So as a quick example, we can have 1/2 O2 plus 1 H2 goes to H2. Oh. All right, we're gonna all right, as an exercise, please write equations for the number of moles of O2, the number of moles of H2, and the number of moles of H2O as a function of the extent of reaction. Just so that everyone is aware. So everyone work this out. I'll give you a few minutes, and then we will go on. All right. Someone tell me what is the equation for NO2? The number of moles of oxygen.
It's the number of moles of oxygen initial.
Which is?
Oh, we start, oh, yeah, 1. Minus 1/2 chi.
Okay. Someone else, hydrogen.
Just 1 minus x.
Yep. And water,
It's 1 plus x.
X.
it's just the eccentric reaction.
Okay.
So then all we need to do now is we need to relate the extent of reaction with some sort of an equilibrium expression. And what we're going to be doing ultimately is this is going to be the delta G of reaction ultimately. Right? We just need to relate what the delta G of reaction is to the extent of reaction, and then we've integrated our phase equilibrium, our reaction equilibrium, sorry, with a single variable. So what we're going to need to find is, how do we get this? How do we formulate it? That's going to be the objective of the next day or so. All right, a few more quick relationships. The total number of moles in the system, right? We're going to necessarily need to know this if we ever need to compute mole fraction, right? So in this case, the mole fraction of species I is going to be the number of moles of species I divided by the total number of moles in the system, in which case the number of moles is going to be equal to the initial number of moles plus the extent of reaction multiplied by the summation of the stoichiometric coefficients. So in this example over here, right, we have 2 moles being consumed, 2 moles being created. The summation of the stoichiometric coefficients is going to be equal to 0. The equation is not going to depend, the number of moles in the system isn't going to depend on the progression of the reaction. In this case here, we have 1.5 moles creating 1 mole. So, according to Le Chatelier's principle, will this reaction be favored at high pressures? Will the forward reaction be favored at high pressures or low pressures? High pressures. Because the system will sort of find a way to equilibrate, meaning if we increase the pressure, that means the system will push itself to having fewer number of moles, and that'll be a way to alleviate the pressure. Right, so we always have kind of a stable equilibrium. Right, so the total number of moles here is going to be given by this expression here. If you are either creating or consuming more moles, that'll mean that the total number of moles will either go up or go down based on the sign of the summation of the stoichiometric coefficients. For multiple reactions, it's the same thing, except we just have 2 coefficients. So if we were looking at a case, let's say, for example, of carbon going to carbon monoxide, which is then going to further react to form CO2, for example. What we would do then is we could rewrite our expressions. In this case, we have 2 equations, which means that we're going to need 2 equilibrium relationships. We're going to need 2 extensive reactions. So in this case, I could call this equation 1. I could call this equation 2. So in this case, the number of moles of carbon is going to be the number of moles of carbon initially in the system minus the extent of reaction 1 minus the extent of reaction 2, because it's being consumed in both scenarios. Oh, whoops. Let me
It should be 1 there.
Well, I wrote it this way to have Carol. I meant to actually do this. CO plus 1 half, okay? And, okay, yeah, there we go. What I drew was an appropriate system as well, but that's actually what I intended. We can do the number of moles of, let's say, carbon monoxide is going to be equal to the number of moles of carbon monoxide coming in. It's going to be formed in reaction 1. It's going to be consumed in reaction 2. So generalizing it, I'm not going to write out all of them. I think you guys probably get the picture. We can generalize this here as the rate of change of the number of moles in the system. It's going to be equal to summation and have a lot of scripts here. In this case here, this is going to be for a continuous reacting system. So if we have a box with things coming in and coming out, this is going to be the rate of change of material flowing in and out of the system, right? How much is species K entering or leaving the system in one of these two streams? N is the total number of moles of the system here. In this case, C is going to be the number of components. In this case here, M is going to be the number of reactions. This is looking at it from a continuous perspective. Okay, that is almost all of the definitions. We've got one or two more. Now, just like with all the other thermodynamics, the key thing to remember here is that what we are teaching is in many ways the system that we've adopted. And this becomes even more so with respect to chemical reaction equilibrium. So, when we did state changes, we didn't know sort of the heat capacity. So that was something that we had to physically, experimentally measure. When it comes to chemical reactions, it's even more complicated. So if I don't know an accurate way using classical thermodynamics to be able to predict what the heat capacity of, let's say, hydrogen or water is, what are the chances that I'm going to know what is the energy stored in that chemical bond? And the answer is we don't. Our classical thermodynamics framework will not allow us to be able to accurately predict that. In order for us to actually understand the energy stored in a chemical bond, we actually need to adopt quantum mechanics. So, quantum mechanics is complicated, and I don't much like it very much. So instead, we just measure it. So instead of having a system to be able to predict this, which is what we would like to have, we actually don't. So for classical thermodynamics and the classical framework, we don't have an ability to actually do this. So the first thing the reference state. This is at 25 degrees Celsius and 1 atmosphere pressure. In the native phase that the pure fluid wants to be in. So what this means, that if we go back to our example of hydrogen, it is going to be a gas at 25 degrees C and 1 atmosphere pressure. Oxygen is also going to be a gas at room temperature and pressure. If these two react, it will form water, which is going to be in the liquid phase at room temperature and pressure. This here is going to be the formation reaction. We are forming a material out of pure atomic species. Oh, sorry, I forgot to say that. The reference state is pure atomic species, which means that if this reaction is being performed at 25 degrees C in 1 atmosphere, this is going to be our formation reaction. So the enthalpy, H of H2, is going to be equal to 0. The enthalpy of hydrogen gas is in its reference state, 25 degrees C, 1 atmosphere, in its native phase. The enthalpy of oxygen is going to be equal to 0. The enthalpy of water is going to be something that's unknown that we're going to physically measure. So the delta H of this reaction is equal to following exactly the same nomenclature that we've used so far, is the summation of the enthalpy of all of the products, final, minus all of the enthalpy of the reagents themselves, initial. So in this particular case here, the enthalpy of water is equal to the enthalpy of the reaction, right? Final minus initial. In this case, the initial is actually all just 0, so it doesn't matter. And we define this as the delta H of formation at the reference state. So, so the formation reaction is where we are creating a molecular species out of the atomic building blocks, which we consider to be our reference state. The little knot up there, that lets us know that we're at the reference state. So, when you built your saturated liquid tables, I don't remember which compound I had you guys do it for. Maybe was it CO2 or was it ammonia? What was it this year? CO2. I told you what to choose the reference state was. Now, I didn't have to do that. I did so that I could compare your answers. But in any real non-reacting system, you all get to have 100% say in what your reference state is. Because the only thing that matters is what's the difference between the inlet and outlet, for example, with the final versus the initial. Now, I don't know how many of you have used a process flow simulator or a thermodynamic software. Who's used something like that? Like Aspen Tech, Promax, anything like that. Have you ever gone and looked at the enthalpy tables? They're all these just really silly negative numbers. And it seems like it's totally made up. That's because the software program probably has some global reference state that makes it so it can be used with reacting systems and non-reacting systems. So in non-reacting systems, we can kind of choose what the reference state is to make it convenient. So sometimes it's nice when we're doing a balance to make it arbitrarily one of the inlet or outlet conditions. In a chemical reaction, no, we cannot change this because it is non-trivial to measure these. Right? You have to do a lot of calorimetry experiments very carefully. So once someone measures this, who cares? Don't rock the boat. Just keep your reference state constant. So all of the formulation for chemical reaction equilibrium is built on this reference state. And hopefully, every source you look at should be using this one, if it's any sort of a modern, reasonable source. But anything that deviates from this, you would basically have to go back and do all the experiments all over again. Because this delta H of reaction is going to depend on the temperature and pressure conditions. So that's why we're stuck in sort of a really small box when we deal chemical reaction equilibrium. We have to adhere to the system, because unless you want to go back and measure all of these, you've got to use what people have already done. It's not trivial to go back and do this again. So, if we have, so one other thing to note here is that this is the heat of formation at the reference state. Now I noted here that this is liquid water. Now for water, very oftentimes it'll be reported with two heats of formation. So we have the heat of formation at the standard state for water vapor is just going to be equal to the heat of formation at the standard state of liquid water plus the heat of vaporization. So water is common enough, used oftentimes, right? If you have water vapor for a saturated mixture. You have to keep track of the state of matter that you're in addition to the chemical bonding itself, right? So we can't ignore everything else we've already done. Okay. The water is really common. You'll see two reported heats of formation for water always, because so often we'll be doing gas phase reactions. Liquid phase water reactions are not particularly common because water is quite stable. But water is used very commonly as a reagent for a lot of chemical processes, but usually at higher temperatures and pressures. All right, so if we look at a different arbitrary chemical reaction, let's say methane combustion. Actually, hopefully everyone didn't cheat already. Okay, let's balance this chemical reaction really quickly. So, where's our starting point? What should we start with? We have a series of elements. We have carbon, we have hydrogen, and we have oxygen. So we need to balance this reaction. So I need to determine the stoichiometric coefficients to make that this thing is balanced out. Where should I start? Carbon. Why should I start with carbon?
Because it's the easiest.
Why is it the easiest?
Because it's only ever, you know exactly where it all goes.
Right, so carbon is only involved in one species on the reagent side and one species on the product side. So we're going to set the basis here on this system that we're going to have one methane being fed to the system, which means that we only have to deal with one CO2 on the other side. Now what's the next one to work with? Hydrogen. So we could have actually started with hydrogen too. So how do I balance this equation with hydrogen? We need two waters. And the last one obviously is oxygen, because oxygen is involved with 1, 2, 3 components. We have to have the other ones balanced before we can deal with it. How many oxygens are required? 2. 1 O2 here, 1 O2 from the two waters, so 2 oxygens. Okay, reaction is balanced. So, what we're going to be doing then is we can write that in this case here, what we are doing, and for the enthalpy balance in the system, is we're going to be creating so from an enthalpy perspective, we're going to have the heat of formation of methane. That's going to be its enthalpy. We're going to have the heat of formation of oxygen. We're going to have the heat of formation of carbon dioxide. We're going to have the heat of formation of water. That's going to be the enthalpy of the inlet and outlet. In case we actually be precise, let's make sure we put the little. We're doing this at the reference state. So this reaction, let's say, is going to occur at 25 degrees C and 1 atmosphere. So in that case, we are going to define the heat of reaction. In this case here, this is going to be at the reference state. We are going to define this let's make sure we'll go over the notation. So we're going to call the heat of reaction the difference between the final minus the initial states, which is just going to be equal to the summation of the stoichiometric coefficients times by the respective heats of formation. So in this case here, this reaction is going to be equal to enthalpy of formation for CO2 plus 2 times the heat of formation, in this case for water in the liquid state, minus the heat of formation of methane, minus 2 times the heat of formation of gaseous oxygen. This one just happens to go to 0. So, who recalls endothermic versus exothermic reactions? So the heat of reaction for an exothermic is positive or negative?
Negative.
So delta H of reaction is less than 0. Delta H of reaction is greater than 0. So what does that mean about the energy of the molecules in the system? So this reaction right here, is this an endothermic or exothermic reaction? So you actually don't have enough information to know based on what I've put on the board, but hopefully everyone knows what this reaction is.
Yeah. It's gonna be
This is the combustion of methane. That's what we use to heat up water and do all sorts of things. This is exothermic, right? We know it gives off lots and lots of heat. If it doesn't give off lots of heat, then basically Peter would be out of a job, right? Producing oil and gas for all of us. So, what exothermic means, right, is that the enthalpy of the products is actually very, very low, and that the enthalpy of the reagents is very, very high. Because the bonds that form, in this case the bonds here are OH bonds and CO bonds. These are low energy. The bonds we're breaking are OO bonds and CH bonds. Now in this particular case here, this one's high energy. What's happening in a chemical reaction is exactly the same thing that's happening in a multi-component system. Right? In the case of, let's say, sulfuric acid and water, when I mix those two together, that's an exothermic process. That's because when the water forms around that sulfuric acid, it forms a really stable low energy state, which basically means that it's got an excess of energy that it needs to get rid of. Now in the case of mixing, that excess energy is going to go to increase the temperature. Same exact thing happens when we're breaking and creating bonds. So we break CH bonds, which are relatively unstable, right? They have a high energy. I create a bond that requires very little energy to create, which means I have a surplus of energy that I have to do something with. Now in the case of combustion, all of that energy goes into heating up the product gases. If those product gases are heated up enough that they start to emit, they will start to emit light because they're so hot that they're exciting electronic energy states, and when those electronic energy states go back down, they give off photons as light. So the flame that you're seeing is emissions from really hot gases. So we can calculate something called the adiabatic flame temperature, which basically means that if all of the energy that we break, the bonds here, goes into heating up the products, we can calculate what the temperature of these gases are, the product gases. Does anyone want to guess what the adiabatic flame temperature of this type of a reaction would be? It might be actually a little bit higher, because this is being burned in pure oxygen. If you're burning it in air, I think it might be closer to 2,000. If you were to crunch the numbers here, you might be looking at like 4,000 Kelvin or something. It's very, very hot. But if we're burning like a candle, you have a lot of air that's being drawn up that's cooling it down. You're forming soot. That soot has a high heat capacity, so it slows things down a little bit. But in this idealized system right here, this is really, really hot. right? And this is another reason why we don't really care a ton about gravitational energy and kinetic energy in chemical engineering, because, right, now let's imagine how much energy goes into boiling something. That's still way more than the potential energy from gravity, still way more than kinetic energy. Now, boiling, so let's say kinetic energy is down here. Boiling takes this much energy. Reactions are like way up here. Chemical reactions consume and release way, way, way more energy than all those other processes. And that's why as a chemical engineer, when we do our material balances and energy balances, we don't really care about the velocity of something going in there. I guess if you're doing like really, really big processes with tons of fluid going through something per second, yeah, maybe it adds up over time, but in general, this is a lot of energy. So one last thing before we depart, and this is what we'll be talking about. We will use the same formulation for the formation reactions and the delta H of reactions. We will use the same thing to define a delta G of reaction, the change in Gibbs free energy. So we will call the delta reaction of the Gibbs at the standard state or the reference state And the key strategy here is we're going to be working with the change in Gibbs free energy of a reaction. But the nomenclature that we're adopting is going to be exactly the same. The challenge is going to be more or less how do we get access to the Gibbs of the reaction. The good news is that's mostly been measured. The bad news is it's not super trivial to get. So basically how we get the delta G of reaction is sort of an indirect way. We have no ways of ever measuring entropy. Entropy is impossible to measure directly, so we always infer it. So anything that has entropy involved, we actually can't measure directly. So how we measure the delta G of reaction is more or less we do, it's sort of like how same thing we measured excess Gibbs in multi-phase systems. We set up a multi-phase system, we define a model, we calculate what the Gibbs has to be in order to satisfy those conditions. Or we can measure, let's say, the delta H of reaction as a function of temperature. That gives us access to information about the Gibbs of the reaction as well. But we can only get access to this indirectly because of annoying little entropy over here. All right, so we will talk about the equilibrium criteria for reacting systems on Friday. And then once we finish up chemical reaction equilibrium, we're going to move on to statistical mechanics. All right, see you tomorrow afternoon at 3 for any homework questions. And have a good rest of the week.